A nuclear-powered aircraft carrier carries a functioning nuclear reactor that operates continuously for many years without refueling, providing power not only for the ship's propulsion but also for catapults, radars, and life support systems for thousands of crew members. How is the safety of such a powerful and potentially dangerous power plant ensured in military operations, including the possibility of combat damage to the ship? The aircraft carrier's reactor compartment is designed with multiple redundant safety systems and a significant structural safety margin, significantly exceeding the requirements for similar civilian power plants. The reactor core itself and its associated critical systems are located deep within the ship's hull, maximally protected from potential external impacts, missile, torpedo, or other combat damage by multiple layers of steel structure and other protective hull elements. The reactors used on modern American aircraft carriers use highly enriched nuclear fuel, which allows the reactor to operate for the entire design life of the ship, typically more than 25 years, without the need for refueling, which would be an extremely difficult and risky operation for a warship on long-term combat duty far from its home port. The reactor control system includes multiple, completely independent emergency protection channels capable of automatically shutting down the reactor upon detection of the slightest deviations from normal operating parameters, an abnormal increase in temperature, pressure, or change in neutron flux long before reaching potentially dangerous values requiring an emergency response. The crew servicing the reactor plant undergoes exceptionally rigorous, multi-year specialized training, significantly exceeding in duration and intensity the training of most other naval specialties, with constant subsequent recertification and regular exercises to practice actions in a variety of emergency and abnormal situations. A separate, important area is protection against the consequences of possible combat damage to the ship. The design provides for the physical separation of the reactor compartment from the rest of the ship by multiple sealed bulkheads, which should prevent the spread of potential damage or radioactive contamination to other parts of the aircraft carrier in the event of serious combat damage in the immediate vicinity of the reactor compartment. There are also detailed procedures, regularly practiced in exercises, for emergency shutdown of the reactor and its complete separation from the rest of the ship's systems in the event of serious combat damage, which should minimize the risk of further spread of an emergency situation even in the worst-case scenario of a real combat engagement. In more than 60 years of operation of nuclear propulsion systems on American warships, there has not been a single serious radiation incident, which the U.S. Navy views as convincing practical confirmation of the effectiveness of its adopted multi-layered approach to ensuring nuclear safety, an approach that combines redundant technical protection systems, exceptionally rigorous personnel training, and a constant, continuous safety culture at all levels of operation of such power plants. After every combat sortie of an F-22 or B-2, technicians conduct a detailed inspection of the aircraft's exterior, often using magnifying instruments and specialized scanners. They're not looking for cracks in the metal in the traditional sense, but for microscopic damage to the radar-absorbing coating, the very material that makes the aircraft undetectable to radar. Why is this coating so fragile, and why is servicing a stealth aircraft so different from servicing a regular fighter? Radar-absorbing materials work thanks to their unique internal structure, often multi-layer composites containing microscopic ferrite or carbon particles arranged in a precise pattern to effectively absorb electromagnetic waves of specific frequencies. This structure is extremely sensitive to mechanical damage. A simple example is a pebble flying off the runway and striking the underside of the fuselage. On a conventional aircraft, this would only result in a small scratch on the paint. On a stealth aircraft, such damage can disrupt the internal structure of the radar-absorbing layer at that point, creating a localized zone of significantly higher radar reflectivity, essentially a tiny window through which an enemy radar receives a significantly stronger reflected signal than expected. Moisture poses a separate and serious threat. Some types of radar-absorbing materials lose their effectiveness when water penetrates the micropores of their structure. This is why stealth aircraft, especially the B-2 Spirit, are traditionally stored in special climate-controlled hangars with constant humidity levels, which significantly increases the cost and complexity of basing compared to conventional aircraft capable of being stored outdoors. Temperature fluctuations also pose a problem. Mechanical stress from the expansion and contraction of the material during significant temperature changes can, over time, lead to the formation of microcracks or delamination of the multi-layer structure of the coating. That's why, after every flight, a meticulous procedure known as low observability surface maintenance is carried out. Technicians literally inspect every square centimeter of the outer surface, using specialized diagnostic tools capable of detecting even minor deviations in the electromagnetic properties of the coating, invisible to the naked eye. Newer generations of radar-absorbing materials developed for the B-21 Raider were designed with this unfortunate experience of the B-2 in mind. They are significantly more resistant to mechanical damage, moisture, and temperature fluctuations, which should significantly reduce the cost and complexity of maintenance compared to previous generations of stealth technology. However, it is impossible to completely eliminate the need for careful monitoring of the coating's condition. Invisibility remains a fragile quality that requires constant attention. Before engineers can claim that a new aircraft is truly undetectable to radar, that claim must be confirmed by precise measurements. How is the parameter called radar cross-section, the number, often expressed in square meters, that determines how visible an aircraft appears to radar measured? The first and most controlled measurement method is testing in an anechoic chamber. This is a special enclosed room whose walls, ceiling, and floor are covered with special pyramidal or wedge-shaped radar-absorbing elements that completely eliminate the reflection of electromagnetic waves from the room's surfaces. Inside this chamber, a miniature physical model of the aircraft, often at a scale of 1/10 to 1/50th its actual size, is mounted on a special support made of a material that minimally reflects radio waves. A special radar inside the camera illuminates the model from different angles, and sensitive receivers record the strength of the reflected signal. Because the camera completely eliminates extraneous reflections, the resulting data accurately reflects the characteristics of the aircraft model itself, not its surroundings. The second method used to measure real, full-size aircraft, rather than scale models, is open-air test ranges known as RCS ranges. These ranges are mounted on a special rotating mast at a significant height above the ground, minimizing the influence of ground reflections on the measurement results. These ranges are often located in remote, deserted areas precisely to minimize interference from foreign objects and ensure maximum secrecy during the tests. The aircraft on the mast slowly rotates 360 degrees, while a remote radar with known characteristics illuminates it from various angles and frequencies, recording the radar cross-section for each specific angle. This is critically important, because an aircraft's actual visibility is far from uniform from all directions. Typically, its lowest visibility is directly in front, where the primary threat from enemy air defense systems often originates, while an aircraft can be significantly more visible from the side or rear. A third method, used after the aircraft has entered service, is periodic check measurements under actual operating conditions, often using specially equipped ground tracking stations or test aircraft equipped with calibrated radar equipment, to confirm that the actual signature of production aircraft corresponds to the calculated and tested values on prototypes and has not degraded due to manufacturing deviations or wear of the radar-absorbing coating during operation. The precise radar cross-sections of modern stealth aircraft remain among the most closely guarded military secrets. Only approximate, often rounded, comparative figures, such as the size of a tennis ball or a small bird, are publicly disclosed, without revealing the precise technical data that could provide critical information to an adversary for developing countermeasures. If ground-based command centers are destroyed by a surprise nuclear strike, Who will issue the order for nuclear retaliation, and how will that order reach strategic forces scattered around the globe? The answer is a special class of aircraft known as airborne command posts, the most famous of which is the E-4B Nightwatch, informally nicknamed the Doomsday plane. Externally, it's a modified version of the wide-body Boeing 747 passenger jet. But internally, it's a flying command center, designed to ensure the continuity of government and military control of the United States even in the event of a full-scale nuclear conflict that destroys ground infrastructure. The aircraft is equipped with electromagnetic pulse, EMP, shielding, special protection for all electronics and wiring from the powerful short-term pulse generated by a nuclear explosion, which is capable of disabling unprotected electronics at a significant distance from the blast site, even without being directly struck by the shock wave or thermal radiation. The aircraft carries a highly sophisticated communications system, including multiple independent channels, from standard satellite communications to specialized submarine communications systems operating at very low frequencies, capable of penetrating even the water column. A specially designed antenna, trailing behind the aircraft for several kilometers during flight, ensures communication specifically with the nuclear submarine fleet, which is otherwise extremely difficult to reach via conventional communications. One of the key elements is the ability to refuel in mid-air an unlimited number of times, which theoretically allows the aircraft to remain in the air for several days straight without landing, ensuring continuity of control during critical periods of conflict escalation. The crew includes not only flight personnel, but also a group of military specialists and liaison officers capable of ensuring the full functioning of the Armed Forces Control Center during flight, including the ability to directly transmit orders for the use of nuclear weapons to strategic forces if ground command is unavailable. In normal, peacetime conditions, at least one such aircraft is kept on the ground at all times, ready to take off within minutes of receiving the order, and historically, during periods of maximum tension during the Cold War, such aircraft were sometimes in the air continuously, taking turns replacing each other, ensuring a 24-hour command post. The existence of such aircraft is a kind of insurance policy for civilization against the worst-case scenario. They are rarely displayed publicly, and most details of their actual equipment and procedures remain highly classified, but the very fact of their constant existence and readiness has been an important part of the strategic deterrence architecture for over half a century. The idea of a combat laser capable of instantly striking a target at the speed of light has captivated the imagination for decades. Military agencies have invested billions of dollars in such developments. But the actual combat use of laser weapons on aircraft remains extremely limited. Why is this technology, seemingly so promising, advancing so slowly? One of the most ambitious early programs was YAL-1, an airborne laser mounted on a modified Boeing 747 wide-body aircraft. The idea was to engage enemy ballistic missiles with a powerful chemical laser during their boost phase, before warhead separation, while operating at a safe distance in airspace. The project faced colossal technical challenges. The laser itself, based on a chemical reaction to generate powerful radiation, required a huge amount of hazardous chemical reagents, which took up a significant portion of the already large aircraft's internal volume, leaving minimal space for anything else. Precisely aiming a laser beam at a target moving at incredible speed over hundreds of kilometers away presented a colossal engineering challenge in its own right. The atmosphere between the aircraft and the target is inhomogeneous. Turbulence, changes in air density at different altitudes, and thermal fluxes all distort and scatter the laser beam, significantly reducing its effective range and target impact power compared to theoretical calculations in a vacuum. The program was eventually cancelled in 2011 after demonstrating limited functionality, but acknowledging that the system's practical combat range and reliability were significantly inferior to initial expectations, and that operating costs remained prohibitive. modern developments have taken a different path. Instead of huge chemical lasers on specialized aircraft, the main focus has shifted to compact, lower-power solid-state and fiber lasers, designed primarily to engage relatively vulnerable, unarmored targets at relatively short ranges, primarily drones and light missiles, rather than full-fledged ballistic missiles. Such systems are significantly more compact, requiring only electrical energy to operate, without the need for hazardous chemical reagents, making them potentially suitable for installation even on relatively small aircraft or land and ship platforms. However, the fundamental problem of atmospheric distortion of laser beams over long distances remains unresolved. This is why most successful practical demonstrations of combat lasers to date have focused on relatively short ranges and relatively small, unarmored targets, a far cry from the futuristic image of a laser beam instantly destroying an enemy aircraft from a great distance, familiar from science fiction. F-15, F-16, F-22, F-35. Why these particular numbers, and why are there no seemingly logical numbers between 16 and 22 in this sequence, much less the huge gap between 22nd and 35? The answer lies in the history of the American military aircraft designation system, which has undergone several significant changes and has not always followed a strictly consistent logic. Prior to 1962, the various branches of the U.S. military, the Air Force, Navy, and Army used their own independent aircraft designation systems, which often led to confusion, especially when the same aircraft type was purchased by different branches under different designations. In 1962, the Ministry of Defense introduced a unified designation system, unifying the numbering system for all branches of the armed forces. It was from this point on that fighter aircraft numbering began anew under this new unified system, which explains why older pre-war and post-war designations bear no direct connection to the current sequence. The gaps in numbering between existing and accepted types are explained by several factors. Some numbers were reserved or assigned to experimental and research programs that ultimately did not result in the creation of a production combat aircraft, but the number was nonetheless used and withdrawn from further use. Other numbers were assigned to aircraft designed for highly specialized, often classified programs, information about which became publicly known much later, or was not made public at all, creating a visible gap in the publicly available sequence. The gap between the F-22 and F-35 is one of the most notable examples of this inconsistency. The program that later became the F-35 was initially developed within the broader Joint Strike Fighter program, and was given the number 35 partly for marketing reasons, to visually and conceptually distinguish this fundamentally new multi-role project from the history of previous pure fighter programs, and partly to emphasize its positioning as a fundamentally new generation of aircraft, rather than simply the next in line. There is also a historical tradition, although not strictly formalized, of starting the numbering of a fundamentally new generation of aircraft with a certain symbolic break in the numbers, reflecting the marketing and conceptual significance of the technological leap, and not simply a mechanical sequence of ordinal numbers. Thus, the seemingly chaotic numbering of American military aircraft actually reflects a complex, repeatedly changing bureaucratic history, a mixture of classified and public programs, and deliberate marketing decisions, rather than random anomalies. A common belief holds that only someone with perfect, 100% vision, without the slightest deviation, can become a military fighter pilot, and that wearing glasses automatically disqualifies one from the cockpit of a fighter jet. To what extent is this true today? Historically, this belief was largely correct. For most of the 20th century, visual acuity requirements for military pilot candidates were indeed extremely strict, virtually precluding any significant vision correction, as in the aerial combat conditions of that time. Visual acuity of the enemy at long range was considered critically important, an irreplaceable factor. However, with advances in technology, modern requirements have relaxed significantly. The current U.S. Air Force accepts applicants with a certain degree of nearsightedness, farsightedness, or astigmatism, provided their vision can be corrected to standard levels with glasses or contact lenses, and the degree of deviation does not exceed established, fairly strict, but no longer absolute, thresholds. There are several reasons for this relaxation. First, modern combat aircraft rely significantly less on direct visual detection of an enemy with the naked eye at long range. This function is now performed by onboard radars, infrared sensors, data from early warning systems, and information from airborne early warning aircraft. The pilot's visual acuity, while still important, is no longer the absolutely critical factor in combat effectiveness it was in the era of classic maneuverable air combat in the mid-20th century. Secondly, the quality of vision correction has improved significantly. Modern contact lenses, and in some cases certain types of laser vision correction approved for military flight personnel, can provide visual acuity virtually indistinguishable from natural, perfect vision, without creating additional risks or discomfort when used in combat aircraft cockpits, under significant G-forces, or during sudden pressure changes. It is important to note that certain types of vision correction, however, remain restricted or completely prohibited for flight personnel, primarily certain outdated or experimental surgical techniques that carry the risk of unpredictable vision changes due to significant changes in atmospheric pressure or the intense physical stress typical of fighter jet flight. In addition to visual acuity, candidates undergo a rigorous color perception test, the ability to accurately distinguish color-coded instruments, signal lights, and indicators, as well as a test of peripheral vision, depth perception, and overall visual reaction speed to moving objects, parameters that, taken together, are significantly more important to a modern pilot than simple formal central visual acuity measured on a standard chart. The myth of absolutely perfect vision as a prerequisite for a military pilot is an echo of a bygone era, no longer fully consistent with modern realities, although certain high vision standards certainly remain an integral part of the rigorous medical selection of candidates for military aviation. Thunderstorms pose one of the most serious natural threats to any aircraft, including the most modern military aircraft. Powerful updrafts and downdrafts within a thunderstorm cloud can create overloads that significantly exceed the structural limits of even the most robust combat aircraft. A lightning strike, although modern aircraft are generally designed with this possibility in mind, still poses a serious risk to sensitive electronics. How do modern military aircraft detect and avoid such dangers? The primary instrument is an onboard weather radar, which operates in a specific frequency range optimized specifically for detecting water droplets and ice particles within cloud formations, as opposed to a conventional airborne radar, which is tuned to detect metal objects. The weather radar displays the intensity of precipitation within the cloud cover to the pilot in a variety of colors on a special display, from green, which indicates light precipitation that is relatively safe to fly through, to yellow, orange, and finally bright red or purple, which indicate extremely intense precipitation and, accordingly, significant turbulence and danger within the cloud cover, which should be avoided rather than attempted directly. In addition to radar, modern wind shear warning systems are capable of detecting sudden, dangerous changes in wind direction and speed at low altitudes, which are particularly critical during takeoff and landing, when the aircraft is in its most vulnerable position in terms of available altitude for maneuvering and correction. Military meteorological services also play a critical role well before takeoff. Specialized units analyze the current meteorological situation and its predicted development along the upcoming flight route, providing pilots with detailed information about potentially hazardous areas even at the mission planning stage, which often allows for route adjustments in advance, avoiding direct encounters with the most dangerous meteorological phenomena. There's also a tactical aspect to weather. Historically, adverse weather conditions were sometimes deliberately used as an element of surprise when planning military operations. It was believed that the enemy was less likely to expect an attack in poor visibility or adverse weather. Modern high-precision navigation systems and automatic instrument landing systems have significantly expanded the ability to conduct operations in conditions that would have been considered completely unsuitable for flight just a few decades ago. However, even with all the technological advances of today, extreme weather events, primarily powerful thunderstorms and associated phenomena such as hail, severe clear air turbulence, and icing, remain one of the few natural factors from which military aviation is forced to retreat, as no technology yet allows for the complete neutralization of the physical danger such events pose to aircraft structure. From the first day of flight school to the moment a cadet first takes the controls of a fully fledged combat fighter, several years of intensive, multi-stage training pass, with each stage weeding out a significant portion of candidates who do not meet the strict requirements. The first stage is basic officer training and initial selection, which includes not only the rigorous medical examination mentioned earlier, but also a series of psychological and cognitive tests that assess decision-making ability, spatial thinking, stress tolerance, and overall ability to learn complex technical disciplines. The second stage is primary flight training on relatively simple piston engine training aircraft. Here, students first master basic piloting skills, takeoff, landing, simple maneuvering, navigation, and operating basic instruments. A significant number of candidates are eliminated at this stage, not so much due to an inability to master technical skills, but rather because of difficulties in decision-making in real flight, which differs from theoretical training on the ground. The third stage is basic jet training on jet trainers, such as the aforementioned T-38 Talon with a new T-7 Red Hawk. Here, the student first encounters significantly higher speeds, the need for faster decision-making, the basics of formation piloting, and the first elements of combat-like aerial maneuvers. At this stage, the critically important assignment to further specialization occurs. Based on academic performance, personal preferences, and, importantly, the armed forces' current needs for specific types of pilots, the student is assigned to either fighter aircraft, transport, bomber, or helicopter specializations. Not every aspiring fighter pilot receives this opportunity. Assignment is largely determined by objective performance indicators from previous stages. The fourth stage, for those assigned to fighter aviation, is advanced training directly on a combat aircraft or a training aircraft as close to a combat aircraft as possible of the specific type to which the student will ultimately be assigned. This includes intensive training in aerial combat, weapons use, group interaction tactics, and actions in complex, emergency situations. Even after successfully completing formal training and receiving a military pilot's qualification, a new pilot assigned to a combat squadron is still far from being considered fully combat ready. They undergo an additional period of adaptation, often lasting several months, within the combat unit, flying under the close supervision of significantly more experienced pilots, gradually being admitted to increasingly complex and demanding elements of combat training before being officially recognized as a fully combat-ready pilot, capable of independently performing combat missions in a real conflict. The entire journey, from the first day of school to becoming a fully combat-ready fighter pilot, typically takes 4 to 6 years of intensive training and practice, and that doesn't even include the ongoing, continuous process of retraining and advanced training that continues throughout a military pilot's flying career. Today's attack drones, capable of delivering precision strikes halfway around the world under the control of an operator thousands of kilometers away, have come a long way, beginning nearly a century ago with much more modest and simple devices. The first radio-controlled aircraft appeared in the period between the two world wars and were primarily intended exclusively as aerial targets for training anti-aircraft gunners and fighter pilots in real shooting at a moving aerial target, without risking human life in the event of a successful hit to such a target. A significant technological leap occurred during the Vietnam War, when unmanned aerial vehicles such as the Ryan Firebee series began to be actively used not only as targets, but also for real reconnaissance missions over enemy territory, where the risk of losing a manned aircraft and its crew was considered unacceptably high. The real revolution occurred much later, in the 1990s and especially the 2000s, with the advent of new generation aircraft such as the MQ-1 Predator, originally designed solely as a reconnaissance aircraft but later upgraded to carry in fire-guided weapons, guided missiles. This was not the result of the designer's original intent, but rather a response to a real need, identified directly during combat operations in the early 2000s, when reconnaissance drone operators, monitoring promising targets in real time, were forced to wait helplessly for a separate manned strike aircraft to arrive to carry out the strike, often losing the opportunity to engage the target during the time required for such a wait. From there, the concept of a strike drone rapidly evolved, culminating in the larger and more advanced MQ-9 Reaper, specifically designed from the ground up as a multi-role strike and reconnaissance platform, rather than simply a retrofitted reconnaissance aircraft. Autonomy was also developing in parallel. The first generations of drones required near constant, uninterrupted operator control at every stage of flight. Modern systems are significantly more autonomous, capable of independently navigating most of the flight path, automatically maintaining a predetermined course, altitude, and speed. The operator's direct intervention is limited to the most critical stages, target detection and identification, and immediately prior to the decision to deploy weapons, which, according to current doctrine in most countries, remains the exclusive domain of humans, not fully automated algorithms. The next stage of evolution, already under active development, is the concept of a swarm, where many relatively inexpensive, small-sized drones operate in a coordinated manner, exchanging information with each other and distributing tasks among themselves with minimal human operator intervention, significantly complicating the task of the defending side, which is forced to deal with not one, but dozens or hundreds of simultaneous, coordinated threats. From a simple towed target for target practice to a potential swarm of autonomous strike vehicles, the evolution of military drones has taken less than a century, and at the current rate of technological advancement, the next significant quantum leap could occur significantly faster than previous stages of this journey have required. Part 7. 70 blocks in total. From the fragility of stealth coatings to the safety of an aircraft carrier's nuclear reactor, each topic reveals its own layer of engineering solutions, compromises, and human effort behind what at first glance appears to be simply impressive military equipment. Military aviation is not a static picture. It is a living, constantly evolving field, where each new generation of technology solves the problems of the previous one while simultaneously creating new challenges for the next. The story continues. And the next chapter is already being written in closed labs and secret testing grounds right now.